presentation is managing environmental data from the field to the map, and I made this presentation for the Soils Conference up in Amherst last week and gave it at one of the sessions there. And so we're going to talk about managing environmental data. We'll start out with kind of a high-level view, and then we'll go from there into setting up a database. Now, we're going to be talking about environmental data like lab and field data for water, soil, air, and so on, and how to manage it and deal with various issues related to that. Starting out with managing field events, preparing for sample events, and collecting samples and labeling them and all that. Bringing the data into the database. Of course, you can't do anything if you don't get it in. And then data review and validation, which can range from just a simple visual review to a full CLP level validation. And then selecting the data you want once it's in the database. And then formatting it for output. And that could be things like, do I want to convert to consistent units? Do I want to compare to regulatory limits? How do I want to handle my flag data and all that? And then displaying the data in various ways, reports, graphs, maps, whatever. And particularly on mapping, I'll spend a little extra time on the GIS side of mapping and how to get environmental data onto GIS maps in various ways. And then finally, the business justification for doing it. A lot of people need to, if they're going to implement a data management system, they need to usually convince somebody to do it. And it's not hard. You can either do a financial justification or a justification based on efficiency and quality or whatever. So we'll talk a little bit about that as well. So starting kind of at the top, you're going to plan your sample events. This is assuming you have some kind of a system in place. Plan your sample events. And it's going to be, are they a one-time or continuous? And then you're going to maybe create a field file, chain of custody, bottle labels and such. You're going to want to have your locations entered. If it's something like an ongoing thing like monitoring wells, if it's not, then out in the field you'll be establishing your locations for soil borings and things like that. And then there's the field and the lab activities, primarily taking the samples in the field and entering any field data. So you might be out there, like for a monitoring event, you might be measuring water levels and pHs and things like that. And then of course, once you're done with that, you're going to bring the lab data into the office or wherever you are, and then of course the lab's going to do their analyses, create an electronic data deliverable for that. And then you've got to manage the data, bring it into the data database, import the data, and importantly, a very important step here is the checking of the data. And I'm talking primarily about consistency checking, but it can also be data types, range checking, and things like that. But if you don't do a good job of enforcing consistency at import time, then you're going to have garbage when you go to get the data out, and nobody wants garbage. So that step, it's kind of funny because we just did a kind of a, it wasn't a proposal, but a response to questions for a big oil and gas company in France, and they wanted to know if the labs could automatically load the data into the database. And every time I hear that question, I just shiver because our clients tell us it's actually most lab files have at least some kind of an error in them. And you got to fix them before you can bring them in. So anyway, I always worry about that. That you need to take the time to get good data, or why bother, I guess is my attitude. And that could be, as I mentioned before, data validation, checking holding times, spike recoveries, things like that. It could be a completeness check. Did we get everything we expected? And then keep hitting the down arrow here. And then that's all tied into the data itself. So within the database, excuse me, we're going to have, in our system, we call them sites, stations, samples, and analyses. So for us, as a site is a project, a location like a soil boring or a monitoring well is a station. On some systems, they're also called sites, but for us, it's a station. And then underneath that are the samples and analyses. And of course, tied into that are things like the parameters could be your analyte names or your physical things that you're measuring or whatever, and all, as well as a ton of other lookup tables, sample matrix, units, flags, that kind of stuff. And then once you have it all loaded, you're going to want to go in, select the data that you want to output, and that could be certain locations, certain dates, certain depths, various parameters, values greater than 1,000, whatever. Choose your display options, and we'll talk more about that later on. Select your output format. Do I want a report, a graph, a map, whatever, or an export? And then you're done. So it's that easy. Good night. No. Okay, so there is more to it. First of all, we're talking about bringing in new data, typically from the field, but you're probably going to have historical data, which can be a bit of a challenge. Either it's in some legacy system or some kind of in the worst case, a wall full of binders that somebody's going to have to type in. And I was talking to a good client of ours. He happens to be in Vancouver, Canada, and they ran into that. A client brought him into their office, and they said, that wall there, that's all of our project data. And he opened it up, and it was all just a bunch of tables from over the years, and they had been Xeroxed 3 times, and there was just no way they could be scanned and OCR'd or anything like that. So he did what he often does with that. He has a contractor in India, and they double enter the data. They have software that compares it, and anything that doesn't match gets kicked out, and they enter it again. And he said at the end of that, their accuracy rate is, their errors are less than 0.1% when they do that. So it's certainly better than most people could type it in. So you got to deal with that maybe. Validation guidelines, GIS data, and then standards or MCLs. For a lot of people, big reason for automating this is for comparison to regulatory limits. And so you got to get those in if you're going to compare it to them. So that's another part of getting the whole thing set up. Now, where are you going to do it? And it used to be it was typically done by putting the client software on the user's desktop, and then the data is going to sit either on their computer, typically in a desktop database like Access, or on a server, which could also be in Access or could also be in server software like SQL Server or Oracle. And the majority of our clients still do it that way. They like to have their data safely inside the firewall, if for no other reason than to be able to tell whoever owns the data that's safe there. But more and more we're having clients that say, I don't want to manage it locally, and I want to put it up in the cloud. Excuse me. So we've been doing that. We use Microsoft Windows Azure, which really, when you set up an Azure site, it looks pretty much just like a Windows server, and you can make Windows desktops through a virtual machine and connect to them through remote desktop. So that works just fine too. So you can either have it locally or up in the cloud, and both work pretty much equally well. So now we're going to move on to setting up the database. So in order to generate good data, you need to enforce consistency in order to get it in. And here's an example of some of the possible lookup tables that you might have in your database. And some of them are pretty simple. The sample matrix could be just a code and a value. It's G for groundwater and S for soil. Some of them are much more complex, like the parameters have a lot of other data elements that go with them. Of course, a big one for a lot of people is the regulatory limits, or MCLs, whatever you want to call them. And so I'm not going to go through all of these. A lot of it depends on what kind of data you're storing too. If you're storing chemical data, you'll have one set of lookups. If you want to store like geology and lithology with the data, then you're going to manage those lookup tables as well. And so once you've done that, here's a simple example. I mentioned the sample matrix is A for air. And in the first one, it's a form view. And the second one, it's a datasheet view, and you can see several of them. Of course, users need to have control of this. They're going to want to make these be whatever they need for their projects. Here's just another example of one. We call them summary categories. So the parameters are going to be associated with these summary categories, either one of them, iron's a metal, or multiple ones. Naphthalene could be both a semi-VOA, and a VOA. So you got to set all these up. And then, like I mentioned, you might have the lithology that you're going to be storing in there. You're going to want to bring in the regulatory limits. And so most people have multiple regulatory limit types. So you might have a federal standard for this, a state standard for that. So here's a drop down, or you might have a risk-based residential, risk-based industrial. So this is the highest level, which is, we call it the limit types. And the worst I've seen is in Texas. It's called the Texas TURP. That's their hazardous materials program. And they have, I think, 160 limit types. So is the source area greater than or less than 30 acres? What's the matrix? What's the pathway? And then within each of those limit types, they might have up to 600 analytes, each of which has target levels. So this can get very complicated. And then once you've done that, then you're putting in the limits themselves. So in this case, we have arsenic for 4 different limit types for one matrix for water. You take an arsenic, you might want to compare it to all 4 of these to see which of the limit types it failed. Typically, you're going to have upper limits, but you might need to have lower limits as well. pH is a range usually. We're showing these as constants, but more and more people are having calculated regulatory limits. And a good example is hardness-dependent regulatory limits, so that the target level is different depending on the hardness of the sample. And we see these done a couple different ways. Some of them are just logical. In other words, if the pH is less than this, then this parameter has to be this. And if it's between this and this, it has to be this. Others are calculated. In other words, you take the logarithm of the hardness and do something with it and use that to calculate the maximum concentration levels. This mess started up in Canada. Now it's dribbling down into the States. And I've seen it in Washington now. I'm not sure I've seen it on the East Coast yet, but calculated regulatory limits. And it's kind of a risk-based thing. It's probably good because it makes it easier to close sites, but makes it more complicated to calculate. So managing your field events, this was kind of on the left of that first diagram. So here we're setting up a sample plan, and we're going to have in this sample plan, we're going to sample 2 monitoring wells, MW1 and MW3. And at MW3, we're going to have a duplicate, a matrix spike, and a matrix spike dupe. We're also going to have create a soil boring, and we're going to have 5 samples, 0 to 2, 2 to 4, 4 to 6 feet for the soil boring. And then you can also do things like set up your container labels. Set up your container programs, print your container labels, create your COCs, and things like that. So we've made some labels. We're going to print them out on some standard Avery label paper. We have our chain of custody. Maybe print that out on 3-part paper you can buy that has red, yellow, or green, yellow, blue, green, yellow, blue. So you print out 3 of each one, and one goes in the cooler, one goes in the shipping documents, and maybe one goes in the logbook or something like that. So you set all this stuff up ahead of time before you go out into the field. All right, so then when the data comes in, you got to import it into the database. And so we're going to start by specifying the file type and format. And there's a drop down for that where we're going to use what we call our data transfer standard 2012 format. But we have lots of other formats, and the user can define your own. So if you have either a columnar format or a multi-table format or even a spreadsheet table, then you can specify how to get it in. And the end result is it all goes into a normalized relational data model of the site, station, samples, and analyses. So once you've done that, you choose your file name, and then there's some settings that you can do here to determine how to check it. And one of the things we've told it is it's going to have to, well, this is not optional. You have to enforce consistency for a number of these required fields. So in this case, we have a site or project called Refining Inc., and we have a station in the lab file that's called MW14, but that's not in the database. So we dropped the drop-down box, and you can see there's an MW14. It's a little hard to see, but there's a dash in front of the 14. So we're just fixing a consistency error between the lab file and the database. And if you don't do this, then you're going to have a very hard time retrieving and displaying the data. And we've run into situations where we have this for both stations and parameters. Sometimes it's very hard to get all this figured out. We did a big project. It's called U.S. Steel Gary Works in Indiana. And there had been like 5 or 6 different consultants, 25 years of groundwater data, 4,000 soil borings. And our client, AECOM, hired us to get all that straightened out and into the database. And there was just so many different things. It wasn't possible to do it interactively like this. So we just sucked it all in, took whatever we got. Once we did that, they had 5 different ways of spelling lead. Now that sounds silly, but there's lead PB, there's lead PB in square brackets, there's LED. So we actually have a feature in our software that lets you choose the name you want to keep, either a parameter name or station name, the ones you want to get rid of, and it moves the data over to the one you want and gets rid of the other ones. So depending on what needs to be done, either way, you've got to have good, consistent data in order to be able to generate good output. So it did it. All your data was handled successfully. And then the next thing that's going to happen is it's going to pop up this activity log. So for many people managing environmental data, the defensibility of the data is really critical. The plume is moving towards the elementary school, or we did one on Air Force Base where the plume had already gotten to the city of Tucson's well field, and they had shut in several wells, and there was going to be lawsuits and all that kind of stuff. So everybody needs to be able to defend their data. So this activity log pops up anytime you change data, and sometimes it knows what you did. So it says I imported 18 records, and I could type in had to fix MW14 again if I want, and save a permanent record of everything that's happened to the database. Now, managing the quality data is really important. The quality of the data is really important. And it can be as simple as just a visual inspection of the data, or it can be in between steps of doing various kinds of checks. We might do a charge balance calculation or run a historical outlier report or something like that. Or you might go all the way up to a CLP level 3 National Functional Guidelines type validation. And actually level 3 is as far as you can go with the lab file. There is a level 4, but that requires taking the case narrative and doing things like reintegrating under the chromatograph curve and things like that. And even though some people claim, yeah, we can do a level 4 validation in the software, you can't. A human has to do that. That's what the rules are. So this is a level 3 validation. It's basically comparable to anybody that does Department of Defense work, what might be considered a SED 2A type data set in comparison. And interestingly, the Department of Defense is finally catching up with the EPA, and they now have their own validation guidelines comparable to the National Functional Guidelines. They just used to use those. Now they have their own, and it's been released, and it's been reviewed several times. They have a conference every year, actually in Florida, Shades of Green, nice place for a conference. And now they're putting out what they call modules for each of the, not exactly methods, but types of tests. So there'll be a module for metals and a module for volatiles and so on. The good news is it's almost the same as the National Functional Guidelines, so it'll be straightforward. I just went to a conference of the Department of Energy discussing those same issues, and they said they will never have standardized validation guidelines because every project wants to do it a different way, and they're okay with that. So our government at work. Anyway, and then once you've done this, a lot of people like to generate what they call a checklist. So what tests did you run? Did it pass or fail? And so on. So, and some of this, to get to this sort of thing, some of it requires answering some questions, and some of it requires running the validation tool and checking holding times, spike recoveries, valid detection limits, those sorts of things. And then the results of those calculations can go on there. And that gets pretty complicated, as you can imagine, when you start bringing in the laboratory QC and you've got your continuing calibration verification samples and all that stuff. But the end result is a report that says what happened. And we actually, on this report, we can do level 4 questions, but the chemist has to do the level 4 validation, and then they can report the results on here. So I guess we could say we can do level 4, but we don't. We just have some reporting for that. Now, I would also say that less than half of our clients do this, which surprises me. But there's a couple of reasons for that. First of all, some projects are just not that critical. We got a little plume under dry cleaners, and it's not bothering anybody. We just got to clean it up. Another reason is that, well, the main reason is that their permit doesn't require it. Or another reason is that some projects require a third-party validation. So the consultant will take the samples, send them to the lab, load them into a database, and then a validator will review the data and assign their validation flags and notes, and then that gets brought into the database separately. So there's a lot of different ways this has to be done, depending primarily on what the project rules are. Now, I've been talking about data that's primarily at the sample and analysis level. So we went and we took a bottle of water, a bucket of muck or something, and sent it to the lab. But there is environmental data that doesn't fit into that data model very well. And I'll give you a good example. The first time we did this was with a client that's trying to build the biggest mine in Nevada. And it's going to be a molybdenum mine. It's called Mount Hope. And they'll get it going once the molybdenum price goes back up. But anyway, in the meantime, they have about 100 monitoring wells around this large property, and they've had level loggers in there taking 15-minute water level measurements for those several years. And they've also been going out once a month and taking physical samples of the water and sending it to the lab to analyze for metals primarily. So what they want to do is to store this, what we call the bulk data, in a database, but you don't really want to drown the samples and analyses with all that stuff. So they're off to the side in a separate table. And then they also wanted to be able to aggregate that bulk data. For example, take a monthly average water level and compare it to the monthly laboratory data. So we would call that time sequence data, and it can handle that. And then another thing is, at the same time we were doing that, some clients said, well, we don't have time sequence data, we have depth sequence data. Excuse me, we're pushing a cone penetrometer or a MIP probe or something like that. So at this one location, we're going to have multiple results going down the hole. So that's depth sequence data. And interestingly, the first client we did that with wasn't really environmental data at all. They were storing exploration data for uranium. And they had actually a pretty cool thing. It was a direct push, direct uranium sensor. It wasn't measuring gamma rays. It was doing something along the lines of what you would get with a mass spectrometer out into the rocks. And so they came up with a uranium-238 in, I guess, grams per kilogram. It's not in rad units like picocuries. It was actually in mass to mass. And so we helped them get that in here by depth. But then they said, well, can we figure out the hot zones and calculate the grade? So that was just a question of writing some clever queries to figure out the top and the bottom of each zone that exceeded a certain cutoff to take to the mill. And then once you had that zone, it was easy to calculate the average of it and use that to basically tell the mill what they were getting in each one of the trucks that was coming in. And then the last two things for this thing is you can store XY data, like we have a client that's dragging a rad buggy around on one of these sites, and they're getting easting, northing, elevation, and total gamma. So that would be 2D data, and you can also store 3D data. Maybe you have an array that's generating a three-dimensional grid of, I don't know, resistivity or something like that. People don't do that in here, though, very much. They just use their geophysical tools for that. So here's just, we clicked on one of the buttons to do a graph over time of, in this case, temperature at one of these locations. So at this point, we've built our database. And now we want to work with the data. And there's kind of three parts to retrieving and displaying this kind of data. And in our terminology, it's data selection, display options, and report type. Now, report's general. It could be a report, graph, map, or whatever, but you start out with data selection. And so in this case, the user's telling it, at this site, Rad Industries, we want these two wells, MW1 and MW3. And as you can imagine, if you fill out one of these lines, it filters based on it. If you leave it blank, you get everything for that particular data field. So we have two locations, and we have a range of dates. In this case, it's a year, and for sulfate. And so I just had clicked on update. It tells me I have 5 sulfate results that fit these criteria. And then I have these various options. I can make a list or report, export graph map, or go out to the Enviro Spase GIS tool. Now the next thing I said, data selection, display options, and we'll get to output type in a minute, but this is a form where the user is telling the software how they want to handle various things. Do I want to display regulatory limits? If so, what? Which limits? Values and flags. So if I have a U flag for undetected, it's telling me I'm about to time out. Hold on. Yes, I want to continue this session. Thank you. It wanted to kick me out. Sorry. Okay, so if I have a U flag because it was a non-detect from the lab, it doesn't have to be a U flag, but that's common. Well, in most places around the country, the regulators want to see it as less than, followed by the detection limit, less than 1.00. But if you're working down in Florida, Florida DEP wants to see the detection limit followed by the U flag. Or maybe you're going to a meeting, you don't even want to get into that, you just want it to say ND. So you need to be able to, by flag, specify how to display each result. So maybe we have a BJ because it was estimated, so you'd want the value followed by that BJ flag. Do we want to convert to consistent units? Do we want dates? Do we want times with them? Calculated parameters. So, maybe I'm coming in from the field and I have a depth to water. But what I really want is a water level elevation so that I can calculate my potentiometric surface. Or the lab has given me B, T, E, and X, and I want my total BTEX. And it could be much more complicated than that, but so it's nice to have the capability of doing these kinds of calculations. I'll give you an example. One of our clients is a Native American tribe in New Mexico, and they happen to be next door to Los Alamos National Lab, which helped make the atom bombs that won World War II. But in the meantime, they made a big mess. And 2 years ago, I guess, they had a fire, and all these trees that had been sucking up all these radioactive isotopes burned and put it off into the smoke and the ash. Well, our client is next door to them. And they were very concerned about this. So they took air samples and sent it to the lab, and it came back with the concentrations of the various isotopes. And then we helped them set up calculated parameters so that each isotope was multiplied by a dose factor. Excuse me, they were added up into a total dose for that air sample. They quickly imported that into the database. The software did those calculations for them. And then they output it to GIS so they would know who to tell that they should close their windows. So kind of near real-time use of this stuff to improve public health. I think that's probably good enough. We'll move on to the next one. So here's just some examples of some of the things that you might output that you might want to generate for various different types of project needs, reports, graphs, tables, that sort of thing. Here's another one. I'll tell a quick story about this one. Another one of our Native American tribes, a guy called me up and he said, my EPA project manager is driving me nuts. And I said, what's she doing now? Every call starts that way. And he said, well, she wants me to graph all my data. And I said, well, that's not a problem. We have it all in the database now. And she said, he said, you don't understand. Every location, every parameter, 900 graphs. It took me 3 months to do it last year in Excel. So we fired up a WebEx. He selected all his data. He ran this report, 100 pages, 9 graphs per page, printed it to a PDF in 10 minutes. So that's probably my best time savings ever. I'd like to brag on that one. Now, other people want to make tables. And tables, there's kind of 2 ways of making a crosstab table. Samples across, parameters down, or vice versa. So here we're telling in this user interface, we're designing a table. And we say, I want my sample information, my station name and sample date across. I want my parameter name and my reporting units down the side. And I want this formatted value and flag result in the cells in the middle. And elsewhere in here, I can go to other tabs and say I want to compare to reg limits and turn on some statistics and stuff. But the end result is something like this. So here's our sample information across the top, our parameter information down. our values here, and they've been compared to 4 different regulatory limits and color coded based on what they fail. And then we also turned on some statistics over here so they can get an idea of what all they have. So this is a pretty typical type of output for a system like this. I know for our software, we've been told about 80% of the data that comes out of the software comes out in something through this tool, some kind of a table along these lines. And of course, the bottom line is that you need to bring the data out in various different ways in order to make project decisions. So here are just a few examples of that. Obviously a graph over time, a little map that has colored dots based on the values. Here's a tree view where you can click down. We have the site, Rad Industries. We have the stations, soil borings. And then underneath the soil boring, we have the results. This happens to be some Rad data. And then this is similar to the one we just saw before. Some people want to see the data on the internet. So this is a simplified version of that select data form. So they're choosing the groundwater monitoring station group and the metals summary category. And then they're going to make a table here. And this is just in the browser. So whatever you have, whether it's a laptop or a tablet or even a phone, by setting it up in a web browser on the internet, anybody can get at the data. So different people have different needs, of course. Excuse me. All right, a couple of minutes on mapping and GIS. So being a geologist, of course, maps are near and dear to my heart, and very little environmental data doesn't have any spatial component to it at all. So to me, mapping it is a no-brainer. It's not to everybody, and hate to tell a story about a client, but one of our clients is the Corps of Engineers. I won't tell you which district. And they had used an older system and had put in a ton of their chemistry data. And the chemists had loaded it, no offense to the chemists. And then they wanted us to bring it into our software. So we started asking about the samples and where they came from. And they said, well, we don't really know that. That software really only starts with the field ID and goes from there. But I said, well, how are you going to put them into GIS? Well, it turned out that all that data had been loaded by a fairly small group of people. And one lady hadn't retired yet, and she knew how to decipher the field sample IDs. And it varied from project to project, but a lot of times it's something like the well name and a dash and the date and a dash. So she knew those various algorithms, if you want to think of it that way, to pick those things apart. And we were able to get from that into something their GIS group had, which was the coordinates of the locations, and pull the whole thing together. But it's not necessarily always easy. And even with that, things like coordinates can be very difficult. One of the first projects I worked on was a big RAD project in the Chicago area, and the 00 of the site coordinate system, I kid you not, was where the railroad used to cross the creek. Of course, creeks move, but so I kind of joke about, it was measured from where the tree used to be, and that's not too far from what we see on some of these older projects. Nowadays, people are using GPS and all that. That's less of an issue anymore, but you still see it occasionally. So you need a base map or image, and the sample locations have to have coordinates, and of course they have to match. And that's not unusual for the well locations to have a GPS, but the base map is in inches from the side of the CAD drawing. So got to get all that stuff figured out. And then GIS software like ArcGIS is used to make the maps. ArcGIS is most common in the environmental business. There are certainly others, Map Info and things like that. But and then there's specialized software to make environmental specific displays. And then integration between the data management and the GIS can save a lot of time and improve quality. So here's an example. The backdrop is a GIS map. The base map came from a CAD drawing. We've got coordinates for the stations, and then we're drawing these call-out boxes, parameters across, samples down, and you can see here we have some exceedances. It's hard to see, but some of those are red. And these are being drawn offside the locations. Here's another one where we've stored some geology in the database, and we're making these stick logs. One track is the concentration, and the other track is the lithology. And we did a project where they figured out that the lithology, that the concentration of the rad material was in the fines, not surprisingly, in the clays and the silts. So they bought industrial log washers, washed off and the boulders, cobbles, it was in glacial till. The boulders, cobbles, and pebbles and all that went back in to backfill, and the silts and clays went in the rail cars off to Utah. So these things can be really useful at times. Here's another example. It's basically that same GIS map, but here we've drawn 3 different parameters on graphs on the map at the locations. And again, these can be really useful to be able to see what things are doing over time and where. And so I'm a huge fan of this graphics way of displaying things. You can look at tables till you're blue in the face, but this tells a much better story. So why would we bother to do this? So I'm looking now at benefits of better data management. And so, this kind of varies, depending on the kind of project it was. But these are some stories that our clients have told us. So they were able to, the way they were doing it before, they had to have pretty high-level people looking at the data and processing it. Now they have those high-level people review it, but the main data management of importing and reporting is done by a less expensive person, lower pay grade. Lower operating cost. So I was talking to one of our clients several years ago, and he said, we're using the software to convince the regulators that certain wells have bottomed out. And once we do that, and they flatlined for 5 years or whatever, they'll let us shut them down. And that saves us about $9,000 the first year, $18,000 the next year, and so on, just by being able to shut down because they're confident that they've solved the problem. And increase efficiency. I told you the story about my friend with the Laguna tribe, but you can save a lot of time by doing this. That's that story. And increasing revenue. We have people who have bought data management software and sold their services managing data for their clients. And there's another thing too, which is these are financial benefits. There are intangible benefits too. I don't remember if I have that on the next slide now. Sometimes I have that. I have a table that I give to people that lets them do calculations like this, but at the bottom it has intangible savings. And those would be things like, one of our clients is Honeywell, the big manufacturing company, and they have an environmental group in India. And they are basically doing some of the reporting and things for their projects around the world because they got great, intelligent, well-educated people over there, but they don't have to pay them as much. And so after they've been running it a while, I was talking to one of the guys over there about it. And in his beautiful Indian accent, I asked him why he was happy they had this. And he said, in his beautiful accent, he said, I get to take a day off on my day off. And then, of course, the other one is just through the whole process, eliminating a whole suite of types of errors, transcription errors. If you go through the field tool, even mistakes, people don't hire their field techs based on their penmanship. So there's a whole set of types of errors that can go away. Now, you can still screw up. I believe people are incredibly creative about doing that, but the software can help. So environmental investigations, they're inherently complex, and efficient data management can improve it. Implementing a centralized system really makes sense for most environmental projects. Tools to do this are affordable and have a high ROI. So I say, is it time to retire your spreadsheet? And then brief word from our commercial sponsor. My company and Tim's company has software to do this. So by my clock, Tim, you said to finish a quarter of. I'm 2 minutes late. Sorry.
That's all right. I think that it went really well. Thank you, Dr. Rich. And I guess this is when we can open it up for questions if anyone has any at the moment.
I had a quick question.
Go ahead.
Sure.
I was all this database and technology and software is very fascinating. I was just wondering, what is the likelihood that things would become completely different even within the next 2 years or so?
Well, the differences that I've seen in the environmental business are not generally the way that the business is done, but what it has to be done to. For example, emerging contaminants. The hot thing right now is PFAS, PFOAs. Before that, it was perchlorate. Before that, it was something else. And really, the process for gathering that data and managing it is pretty much the same. The move towards the cloud and towards wanting to do these things on the web is definitely a direction that things are going. But it's not going to be 2 years. It could be 5 or 10, I suppose. But yeah, things always change. But I would say that anybody that generates a skill set for doing this sort of thing, they're going to have to adapt, but they're not going to have to give up and start over. That's been my experience. We sell commercial software to do this, and it's improved and evolved over the years, but deep down inside, it's about the same way it was 20 years ago. And I wouldn't be surprised if it'll be about the same way in 20 more years. It's just, you got to do what you got to do, and that part doesn't change much, I don't think.
I understand. Thank you.
Sure. I like questions. Who's got another one?
I've been wondering this time about the cone penetrometer that the companies are using on their for the soil borings. What is that tool?
Okay, so a cone penetrometer is it's attached to a geoprobe rig, which is basically a big hammer that drives things into the ground. And you can drive lots of things into the ground. And a cone penetrometer is basically just like it sounds. It's a cone that goes on the end of a metal rod, and you drive it into the ground with a certain amount of pressure. You hit it with the hammer with a certain number of psi, certain number of blows per minute. They call it the blow count. And then you see how far it penetrates. So the harder you hit it and the more times you hit it, you figure out how far down it goes. And it basically tells you, it tells you the penetrability of the material, but that, if you've got an idea what the material is, which you would for the soil boring, you can use that to calculate things like the bulk density. And it's used a lot in engineering work because if you're going to put a bridge there, you want to know how it's going to compress when they drive semis over it. It's also used in environmental work because if you really know what you're doing, you can use the output of the cone penetrometer to get a general idea of what the transmissivity of the materials are. So for example, if you've already done a soil boring and you know you've got 20 feet of clay and then 10 feet of mixed sands and silts and clays, then as you're driving through that material, it'll go faster generally through the porous zones. And so by looking at where they are and how thick and how many there are, that can give you an idea of what the hydrogeologic regime is down there. So if, for example, you start pumping in stuff to chemical oxidants or bioremediation chemicals or something like that, you've got a general idea of where they're going to go. So the cone penetrometer, like I said, is mainly an engineering tool, but it's also used in environmental to get an idea of the rock properties down below. I mentioned one other as a MIP probe, and that's more of an environmental tool. It stands for a membrane interface probe, and you drive that down into the ground, and it basically tells you the amount of organic material you're going through. So if you do a cone penetrometer and you figure out where the porous zones are, and then you run a MIP probe down there, you can figure out whether that porosity has, for example, NAPL in it or something like that. So combination of these tools can give you a pretty good idea of what's going on down there, which obviously you got to know what you're doing. How's that George Harrison song go? If you don't know where you're going, any road will take you there. Well, that's certainly true of environmental remediation. And you got to know where it is if you're going to fix it. And so that's what those things are.
Thanks. Yeah, that helps.
And my thanks to Tim for being willing to sit through this twice. He came up to UMass and watched me give it there, and then set this up tonight. So he gets the attaboy for being willing to tolerate this twice.
Well, it's recorded. So
I have a question.
Go ahead. Sorry.
Yeah.
Sorry, okay. So I understand there are two things. There is data collection and then there is data management. So for people who are doing data management, is it mandatory to have good experience in data collection?
Not really. A lot of our clients, it's pretty much broken up. The data collection is done by the field techs who may have an environmental degree. They may not. They may be geologists. They may just be field techs. So no, they just collect the samples and send them in. And then whoever's going to manage the data has to understand things like interaction with the laboratory, make sure that they can give you a good file, how to load it and maintain the consistency and things like that. And then there's another set of skills for if you're doing validation for the chemist to look at it. But no, if you want to manage data, you can do that almost in a vacuum. Now, obviously, the more you know about the whole process, the better, especially when there's problems. But no, the field techs are pretty separate from the database group, although in most companies, the database group is, well, I shouldn't say that. In a lot of companies, the database group is part of the project. Now, not always. I talked to a lady up at UMass, and their company has a data management group out in the state of Washington. I know them well. They don't use our software. They like to write their own tools. I won't make a comment about that. But she said to me, I need to export data in New Jersey DEP format, which is an ugly format, and I can't afford to use them. Can I use your software to import my lab data and make a New Jersey DEP format? So Tim is working on setting up a demo to show her how to do that. The various groups can be very separate, or we have some of our smaller clients. One of them happens to be here in Colorado, and it's one guy. He goes out and takes the samples. He interacts with the laboratory. He brings the data into the database. He generates output. He outputs the dump stat to do statistics, sends it out to Enviro Spase to do the GIS. So it varies, but no, it can be very compartmentalized. I wouldn't worry too much about needing to know more stuff than you want to know.
Okay, all right. And then you said that the lady was about to write her own software. So aren't there very standardized things? Like you said, the small businesses have their own thing. So is there a certain standard that this is the language in which everybody who's exchanging the data, they need to communicate?
Well, that's a great question, and it varies depending on the process and the regulators and all that. The first is the transferring of the data. And most systems, like our commercial system, has a recommended format for the laboratory. Also, for example, the Department of Defense, and more now the EPA, is using a format called SED, Staged Electronic Data Deliverable. That's an XML format. So in terms of moving the data around, there are a variety of standards, although as soon as the EPA and the Army came up with SED, the Navy said, great, a standard, we'll make our own. They call it NED. So they took the standard and changed it. So it's a mess. And then once you bring the data in, a lot of people just use Excel. The smaller projects, they'll just take the lab file, bring it into Excel, get out their highlighter and determine their exceedances. And, you know, if you've got a couple monitoring wells, you're sampling once a quarter, that's good enough. But if you want to do more efficient data management, especially on larger projects, you're going to need an application. And your options are buy one off the shelf like ours, which is, of course, what we're in favor of, or build your own. And we see people that build their own. We've replaced many of those, many places over the years. Small and large companies have decided they're smarter than professionals. They're going to do it themselves, and it may take a year. We had one client that I went and visited them in New Mexico, and I showed them our software, and they said, that's cool, but we just hired a summer intern. He's going to write us a database. And so I thanked them and left. I had already bought them donuts. And I called back a year later, and they said, oh, yeah, he quit. We never did get that done. And they ended up buying our software for 3 of their offices. So building it yourself is not particularly a good plan, in my opinion, but your mileage may vary. If somebody thinks that they have enough experience to make up for our doing this for 20 years and can do it better, that's not why they do it. They do it because they think it's going to be cheaper. But it's much cheaper to just buy it once and use it forever than to spend the whole rest of your life adding features that some other project manager wants.
Great. Thank you very much. Thanks. No, and unfortunately, I couldn't log in from my laptop today, so I've missed the presentation. Tim, can you send us a copy of this presentation if Dr. Hitz allows that?
Yeah, I said that's fine, and I think Kelly recorded this, so she should be able to send you a recording. All
right, great. Okay. Thank you, Dr. Hitz. Thanks.
Also, anybody that wants the slides themselves, reach out to Tim. And Tim, on that piece of paper that I handed out there from the booth, I've got the address to this. I don't think it's up on our website, but I don't think it's on our white papers page yet. But anybody wants the slides themselves, we'd be glad to get them to you also. But then you don't get my wonderful narration.
Thank you so much. Appreciate it.
I'm glad she knew that was a joke.
Great.
And I have time for you. We get any more questions, or I have time for a joke? All right, I'll tell a quick one, then maybe we got time for one more. All right, so actually it's based on statistics. So you may have heard that New Jersey has the most hazardous material sites in the country, and Washington, D.C. has the most lawyers in the country. And can you tell me why that is? And the answer is that New Jersey got to pick first.
Ah, ha, 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 ha.
When I told this up at you,
I am in New Jersey.
oh, are you? But you're not a lawyer.
Yes. No, I'm not a lawyer.
All right, you're okay then. All right, so another question, or we can be done.
I just think it's probably worth mentioning, like the sort of the applicability of the data, just data management in general. Like I think most of our examples are like remediation, but I know we have other people like doing agriculture, probably some people doing some sort of biological research. Can you touch on that?
Yeah, so actually that's funny because we're signing up a new dealer in, of all places, Nigeria. And just got our software. I've been doing the training, which means getting up early in the morning to do it during their day. And he asked for a list of things that we could apply this software to. And he gave me some categories. So mining, it can be used for both the mining process itself and also monitoring around the mines and that sort of thing. Petroleum can be used for pre-drilling baseline sampling, can be used for spills around the well site. It can be used for managing the effluent of the oil wells or of the refineries. It can be used for spills around pipelines. As Tim mentioned, we have agricultural users, biological users, basically anything that kind of has a location and a value. And there's a lot of it, because that's the key. If you only have 10 numbers, it doesn't matter how you do it. But if you have 10 million numbers, which a number of our clients do, you better have a structured way to do it, or you're going to be in big trouble. By the way, our administrator was not happy when I said I was going to sell our software to Nigeria, having heard of all the Nigerian scams over the years. Where your aunt has died, and we're going to send you $10 trillion, and you have to send me a nice pair of black shoes, that sort of thing. But he wired us the money first. It turns out he's really, really smart, straight up guy. He owns an environmental lab in Nigeria, and also does environmental consulting there. So I think he's going to be a fun client to have. So you can't prejudge.
True. Doctor, can I also ask you, you mentioned about being in touch with people in India. Which part of India are they doing a project, or if you are associated with that project?
Well, I did work on that project, but to tell you the truth, I didn't go there. We did all the training via WebEx, although I got the impression that they might be in a couple of different places, but I really honestly must say I don't know.
Okay. All right. Okay.
Somebody asked a question about what things are going to be changing in the future, and the simple answer is it's not going to matter where anybody is. Our company is a small company. There's only 8 of us, but we're in like 5 different locations. Most of our people work in their fuzzy pink slippers from their homes, and we even had to downsize our office here in Denver because most people don't come to the office. Tim's never been to our office. A number of our consultants have never been to our office. So yeah, so where people are is, and especially now with the cloud, it's even less important. People say, where's my data going to be? And the answer is, I don't know or care. But I'm sorry, I understand why you asked, because it sounds like you may be from there, and I apologize for not knowing.
No, I am from India, so I was just curious to know, like, if you're working on a project, which part, or what kind of a project. So that's what.
That's interesting. The projects are not in India.
Okay.
The projects are scattered all around the world. Every place that Honeywell has plants, and they hire contractors to take the samples and send them to the lab, and then the lab data goes to the people in India who all have college degrees and very knowledgeable about this stuff, and then they do the data review, the data selection, and the reporting, particularly for regulatory purposes. So no, the projects are scattered all around. The people that are doing the work are in India.
Oh, I get it. I get it. Okay.
Yeah, this has been a great presentation. I think that you've given a lot of terms and some of the just the wealth of data that you're able to put into these and the way that they're tailored to the specific projects is very interesting. So as a follow-up to that, if anyone has questions that we're not able to answer tonight, if you have more questions about some of the tools that are being used or even some of the acronyms that are being used in the way the data are processed and then stored in these databases, we can always bring that up at another environmental lounge. But thanks so much for your time tonight and being willing to share this with our students.